Hello, Matthews, Gatos here. Welcome to this video for chapter number 6, Polynomial and Sinusoidal Functions. And we're going to be doing lesson number 1, which is dealing with polynomial functions of degree 0, 1, and 2. So this is a review lesson because we have done degree 0 and 1 in 10C, and then we've done degree 2 in our 20 level courses. So hopefully everything on here is a review. A lot of terminology to get through, so bear with me. So in this chapter, chapter 6 is split into 2 sections. The first couple sections is on polynomials, and the last couple sections is on sinusoidal functions. But it all really comes down to the graphs and analyzing the graphs. So let's start with polynomial functions. A polynomial function consists of one or more terms which are separated by adding or subtracting. So we've already dealt with polynomial functions before. For example, f of x equals x squared minus 4x minus 5. That's a polynomial. It's a quadratic. 2x minus 4, that's also a polynomial. It's a linear function. And f of x equals 3 is also a polynomial function. So the big thing with polynomials is that if you have an x, the exponent is a whole number. So see, the exponent here is a 2, invisible exponent of 1, invisible exponent of 1. This one here, the x has no exponent, so it actually has an exponent of 0, which again is a whole number. The degree of a polynomial. The degree is the value of the highest exponent in the function. So the highest exponent in the function. So for example, if I have x squared minus 4x minus 5, the degree is 2. In this polynomial, 2x minus 4, the degree is 1, the highest exponent, which is the invisible one. What about this one? F of x equals 3. I could rewrite that as 3x to the 0, and in that case the degree would be 0, because constant functions have a degree of 0. Now, if the polynomial includes a term with no variable, so no variable, that's called a constant term, also the y-intercept. Now you need to pay attention to signs. So here you can see that the one without a variable is negative 5, so the constant term is negative 5. In this equation here, the constant term, the one without a variable, is negative 4. And in this one here, 3 is the constant because there's no variable. That's why it's called a constant function. Okay, now let's talk about coefficients and leading coefficients. So a coefficient is any number that multiplies by a variable. So really it's the number in front of a variable. Now that's what a coefficient is. The leading coefficient, however, is the number that multiplies the term with the highest power. So it's the number in front of the variable with the highest exponent. So in this example here, look through all the terms. X squared is the one with the highest exponent, and the number in front of that is an invisible 1. So the leading coefficient is 1. Looking at this function here, linear function, this is the term with the highest exponent of 1, x to the 1, and the number in front of that is 2. So the leading coefficient is 2. In a polynomial function, all the coefficients have to be real numbers. So you can't have anything causing you to divide by 0 or square root a negative. So I want to write a polynomial function that satisfies the following conditions. Now it's important that you note answers of course can vary. So I'm just going to come up with like the most basic answer, but you could come up with something that's a little bit different. So I want to look at a degree 2 polynomial with a leading coefficient of negative 3. That means I have an x and the highest exponent is 2. I could have other things around that, but I can't have anything with a higher exponent of 2. The leading coefficient is negative 3, which means there's a negative 3 in front. So I'm going to go with the most basic answer, negative 3x squared. You could add on a number, add on an x and a number. I'm just going to stick with the most basic. So this next polynomial has a degree 2, leading coefficient of 7, and 2 terms. So degree of 2 means x squared is the highest. The leading coefficient is 7. The number in front of the term with the highest exponent, and there's 2 terms. So I could add or subtract anything on there as long as it's not higher than an x squared. So for example, I could subtract a 4 or a 4x. Next one, degree 1, leading coefficient 1. So degree 1 means it's x to the exponent of 1, and there's a 1 in front. So that would be my most basic answer. But I don't necessarily need the ones, so I can just say f of x equals 1, because the invisible 1 is in front and the invisible 1 is the exponent. Okay, degree 0, that means I have x to the 0. So I have to have a number in front of that. Could be a 1, could be a 2, could be a -7, could be anything that you wanted to. Let's do -7. So I could write it like that, or I could just say f of x equals -7. Okay, next one, degree 3 and a constant term of 8. Degree 3 means x is the highest exponent with 3. And I could add on anything I wanted there as long as it wasn't higher than an exponent of 3, and it has a constant term of 8. So I'm just going to keep it nice and simple, x cubed minus 8. But again, answers can vary as long as you satisfy those conditions. Okay, now we're going to go through an investigation of degree 0, 1, and 2. And in the next lesson, we'll talk about degree 3. So, polynomial function f of x equals 3 is shown in the graph below, or to the right. So I want to state the domain and range. So the domain, if you look at all along here, it can be any number at all. So x can be any number. So we say it's the set of all x such that x is an element of the reals. Now let's look at the range. Because it's a constant function, y is always 3. So the range is the set of all y such that y is just equal to 3. Let's write two other functions that have a degree of 0, which could be graphed on the same grid. You could have any possible answer. Here's an example, f of x equals 5. So that's just a horizontal line passing through 5. I could have f of x is -2. So that would be a horizontal line running through a y value of -2. Describe the general shape of each graph. Well, you can see that each graph is a line, but not just any line, it's a horizontal line. So those are some of the properties of degree 0. Now, the number of y-intercepts that each graph had. If we go back here and look at our graphs here, we can see that the number of y-intercepts are always 1, 1, 1, and 1. They all have a y-intercept of 1. Do any of your graphs have an x-intercept? Well, not the ones that I graphed. So horizontal lines really have no x-intercept. If you think of any horizontal line going through, it's always going to have one y-intercept and no x-intercepts. The only exception is if I pass through the x-axis. That is the only example where I don't just have one x-intercept. Let's change that. It's actually not one x-intercept. It's an infinite number of x-intercepts. So that's the one exception there. Okay? Every other horizontal line does not have an x-intercept. The only one that does is f of x equals 0 or y equals 0. That has an infinite number of x-intercepts. Now, describe the relationship between the equation of each function and the range. Well, it would be the same because the range is the y equals to the number it passes through, y equals to the number it passes through. So the equation and the range will always be the same. Okay, let's generalize all polynomial functions of degree 0 in the form f of x equals c. So c can be any constant number. So this is a graph called a horizontal line. Horizontal lines again have 0 slope because there's no rise. The domain will always be the set of all x such that x is an element of the reals, and the range will be y equaling to that constant, whatever it passes through. There's always going to be 0 x-intercepts with the exception of the function f of x equals 0. That one has infinite number of x-intercepts, and there will always be one y-intercept. So does the value of a polynomial of degree 0 depend on the value of x? Well, no, because degree 0 means there is no x value. Since the values of the polynomial of degree 0 remain constant for all values of x, this type of function is called a constant function. Constant because the value of y is never changing. Okay, let's switch it up to degree 1. So all of these functions here are degree 1, and they have lots of things in common. Let's look at some of the things that I came up with. If you look at these graphs, they all have one x-intercept. They all have one y-intercept. They're all lines, and those lines are of the form mx plus b. They all have domain where x can be all real numbers because these arms extend infinitely in both directions. So I'm going to cover all the x values and also all the y values. This is true of every degree 1 polynomial. Now, how does the constant term relate to the characteristic? The constant term, look here, constant term of 2, y-intercept of 2. Constant term of -4, y-intercept of -4. So the constant term, the b value, will always be the y-intercept. So how can you tell from an equation of a polynomial whether the line increases or it decreases? Well, that has to do with the slope, or what we like to call the leading coefficient. So if the leading coefficient is positive, I'm increasing. If the leading coefficient is negative, just like a negative slope, I am decreasing. Okay, so polynomial functions g of x and h of x are parallel lines. How can I tell that those are parallel lines? Well, if you look at that, let me just make that a little bit less blockish so that we can actually see through it. Let's just try that again. There we go. Okay, if we look at those, we can see that the number in front, -1/2, is the slope. So they are parallel because they have the same slope. So how can we tell equations are parallel? They have the same leading coefficient. So in general, what function of the graph is represented by the leading coefficient? The leading coefficient is the slope. So if I have the same slope, that means I run in the same direction and those lines will never meet. Okay, so let's generalize about degree 1 polynomials. So those are always in the form mx plus b. So the shape of these graphs will be a line. They will have a slope in front of x, the leading coefficient of m. The domain will always be the set of all x such that x is an element of the reals, and the range also the same. Always y, the set of all y such that y is an element of the reals. There will always be one x-intercept and one y-intercept. And that y-intercept is the constant value, or in this case, the b value. Now, the direction of the line is determined by the value of the leading coefficient. So if the leading coefficient is positive, the line slopes from quadrant 3 to quadrant 1. If the leading coefficient or the slope is negative, the line slopes down from quadrant 2 to 4. So since the graph of a polynomial function of degree 1 is a straight line, this function is called a linear function. So hopefully that's all coming back to you from 10C. Let's move up to our 20 level courses and look at polynomials of degree 2. So polynomials of degree 2 are called quadratics. So here's 4 different examples of quadratic graphs. And you know they all have that U-shaped graph. And that U-shaped graph has a name, and it's called a parabola. So that's what a parabola is a U-shaped graph. So let's look at some of the properties here. So from this list of characteristics, which one is the same for every single graph? So I remember that all of these graphs, since the arms extend infinitely in both directions, they're going to cover every single x value. So the domain is going to be the same. The domain of every parabola is going to be the set of all x such that x is an element of the reals. Now the range, you can see these are all different. Here's a low point and it's above. This one has a high point and the range is below. So that's not the same. The number of x-intercepts, also not the same. Like this guy here has 1 x-intercept. This one here has 2 x-intercepts. Look at this guy up here. He has no x-intercepts, so those aren't the same. But they all have at least, no, exactly 1 y-intercept. So you always have 1 y-intercept. And how does the y-intercept of the graph relate to the equation? Remember, that is your constant value. Constant value of 10 here, y-intercept of 10. Constant value of -8 here, y-intercept of -8. So the y-intercept will be the constant in unfactored form. So if it's in unfactored form, it's just the number all by itself. If it's in factored form, we have to let x be 0 and then solve for y. So just a little bit of an extra step. Okay, so parabolas can open up or they can open down. And they all have one turning point, and that turning point is a max or a min. So how can I tell just looking at the equation if it has a max or a min? Well, if I look at the leading coefficient and it is positive, it opens up. So if it's positive and it opens up, it has a minimum value. And if it has a minimum value, that means that the range is everything above that minimum value. So it's a set of all y such that y is greater than or equal to that minimum value. Now let's look when the leading coefficient is negative. So when it's negative, it's been reflected in the x-axis and it opens down. So a leading coefficient is negative and opens down, which means that I have a high point, a maximum, which means my range is everything below that point. So the set of all y such that y is less than or equal to the maximum, where y is an element of the reals. Okay, so looking at these graphs here, we want to look at some of the things that that you can determine from the equation. Okay, so in these examples here, you can have a quadratic can have 0, 1, 2, or 2 x-intercepts. No more than 2 because that's the degree. Okay, so these functions are written in factored form. So let's look. This blue graph right here, this blue graph here, written in factored form is x plus 1, x minus 5. Now you can see that that graph there has 2 x-intercepts. 2 factors, 2 x-intercepts. Now let's look at the x-intercepts. The x-intercepts are here at -1 and here at +5. So -1, which is the opposite of x plus 1, and at +5, which is the opposite of x minus 5. Okay, the red graph, this red graph right here. This one here is written as the equation -2x squared plus 8x plus 10 is factored as -2x plus 1, x minus 5. So again, I can see that there are 2 factors, which means I have 2 x-intercepts. So those 2 x-intercepts are going to be at my opposite sign. So the opposite of a +1 is a -1. The opposite of a -5 is a +5. And the last graph, the one drawn there in green, is factored as 2x minus 2 squared. So you can see I just have that one x-intercept, and that x-intercept is at the opposite of -2, +2. So we can use those opposites to come up with the value of the x-intercept, and the number of factors is just going to be equal to the number of x-intercepts. So as I mentioned before, the degree of a function is the maximum number of x-intercepts. So I can have 0, 1, or 2 x-intercepts, but the number of factors will be the number of x-intercepts. Okay, let's look at the first example here. Can you believe all of those notes and definitions? And we're just now at the first example. Okay, let's look at the function p of x is equal to 7, x minus 1, x plus 1. So looking at that, I can see the leading coefficient is positive, so I am opening up. Because I'm opening up, I know I have a minimum. So x-intercepts, there are 2 factors, 2 x-intercepts. The values of the x-intercept, opposite of a -1, +1, opposite of a -6, -6. And the value of the y-intercept. So because this is in factored form, I just replace my x's with zeros, and I'm going to get 7 times -1 times 6. My y-intercept is at -42. Okay, my red graph here. My red graph opens down because the leading coefficient is negative. Because it opens down, that means that I'm going to have a max. So p of x has a min, and q of x has a max. The number of x-intercepts. There is only one factor there, so I only have one x-intercept. And that x-intercept is the opposite of a +1 is a -3. Sorry, +3. The opposite is a -3. The value of the x-intercept, let x be 0 and solve for y. So I'll have -3 squared, which is -9. Okay, so a lot we can tell just from the equation in factored form. Let's talk about the end behavior. The end behavior is what happens at the left and the right tail. In other words, as it extends further and further in each direction. I like to say, as x approaches positive infinity, what's happening to the y? As x approaches negative infinity, what's happening to the y? So when I talk about the behavior of a graph, I'm really talking about my y values. So let's go and do the end behavior of each of the graphs that we've done. So when we have degree 0, that's a horizontal line. The end behavior extends from quadrant 2 to 1 if it's a horizontal line up here, or from 3 to 4 if it's a horizontal line there. Degree 1. So mx plus b. It's a degree 1. If it's a degree 1 and the leading coefficient is positive, such as this, then I can see that the right tail is going to be pointing up and the left tail is going to be pointing down. In this example here, when the leading coefficient is negative, right here in C, you can see that the right tail is actually pointing down and the left tail is pointing up. Notice that the tails are pointing in opposite directions when the degree equals 1. So they have opposite end behavior. Let's talk about degree 2. So degree 2, again, is a polynomial tied to the leading coefficient. So the leading coefficient, if it's positive, then just like in figure D, it opens up. So since it opens up, both of the tails, left and right, go up. If the leading coefficient is negative, just like in figure E here, it opens down. And if it opens down, the left and the right arms are opening down or pointing down. You'll notice when I have degree 2, the tails go in the same direction. So they are both up or they're both down. They go in the same direction. Okay, let's look at some equations here. So using what we know about all of these. So f of x is negative 2x plus 4. So that is a linear graph with a negative leading coefficient. So if you think about that, that is a line, a negative leading coefficient. It's going to have a negative slope, so it's going to look something like that. So looking at my equation here, my left tail is going to be pointing up. My right tail is going to be pointing down. The nature of the turning point, linears have no turning point. They just extend infinitely in both directions. Okay, let's look at the next one. 2x squared minus 7. So because the leading coefficient is positive, I know that my parabola opens up. So because it opens up, my left and my right tail are both up. It opens up, which means it has a low point, a minimum point. Okay, this one here is a linear, negative 5 plus 3x. It's just jumbled up. But the leading coefficient is a positive 3, so I know that my line goes something like that. So based on that, I can see that my left tail goes down, my right tail goes up. And of course, I don't have a max or a min, no turning point, because it's linear and it extends infinitely in both directions. Okay, let's look at this last one here. Again, this is a quadratic just in jumbled order, but you can see that I have a negative leading coefficient, which means my parabola opens down. Because it opens down, both of my arms are pointing down. Because it opens down, I have a high point, so my turning point is actually a maximum. So I did that all without putting them in the graphing calculator, but there's nothing to say we couldn't have put it in the graphing calculator. So I just want to check to see if we're right. So f of x, yeah, going in that direction. G of x, opening up, yes. H of x, positive slope, and k of x, opening down. So it looks like just using the properties that I've learned, I can come up with the sketches without putting them into the calculator. But you can always look in the calculator as well. So to summarize, degree 0, horizontal line. For any kind of a function, the y-intercept is always the constant. If I have degree 1, it's an oblique line. What I mean by oblique means not horizontal and not vertical. So it's kind of on a diagonal. So it's not horizontal and it's not vertical. Okay, again, the constant is always the y-intercept for degree 1. For degree 2, quadratic function, the leading coefficient determines the direction of the opening. Positive is up, negative is down. The constant is in unfactored form is the y-intercept. If it's factored, you let x be 0 and solve for y. So that's the end of our lesson for lesson number 1 reviewing. In the next lesson, we'll look at lesson 2 But I just wanted to do a shout out to parallel lines. They have so much in common. It's really a shame they'll never meet. Okay, I hope this lesson helped. I will see you for the next one.